Right now, tonight, there is a boundary around everything you will ever be able to see. Not a wall, not an edge in space, a horizon. The same way the ocean has one, except this horizon is made of time itself, and beyond it lies the one thing every civilization that has ever existed has wanted to know. What's out there, past the edge of what we're allowed to observe? Here's the part that should unsettle you. That boundary isn't fixed, it's closing in. Slowly, silently, entire galaxies are being carried past it every single day, vanishing from our reach forever. And one day, far in the future, whoever or whatever is looking up from Earth will see nothing at all. No galaxies. No proof the Big Bang ever happened, just an empty, silent sky, and no way to ever know it wasn't always that way. But here's the twist that makes this stranger than a simple countdown to darkness. Even as our horizon shrinks toward that empty future, our tools for measuring it keep getting sharper. Sharp enough that in the last year alone, the James Webb Space Telescope pushed the edge of what we can see back further than anyone expected, and found something there that wasn't supposed to exist yet. And separately, painstaking measurements of the shape of space itself have handed us a genuine, mathematically serious clue about what might be sitting just beyond the part we can reach. This is the story of the cosmic horizon, the boundary that's disappearing right under us, what we just found at the very edge of it, and what the math says is almost certainly still out there, forever out of reach. If you can't stop wondering what's out there, subscribe to Big Data Vault. The search has only just begun. Every horizon needs someone willing to sail toward it without knowing what's on the other side. And Cosmology's version of that story starts with a man measuring blurry smudges of light through a telescope in the 1920s. Edwin Hubble wasn't trying to define the edge of the observable universe. He was trying to settle a much smaller argument. Were the faint spiral-shaped smudges astronomers had been cataloging for decades actually part of our own galaxy, or entirely separate galaxies in their own right, sitting impossibly far away? Using the 100-inch telescope at Mount Wilson, Hubble identified individual stars inside one of these smudges, the Andromeda Nebula, and calculated it was over 2 million light-years away, far beyond the known edges of the Milky Way. The universe, in a single measurement, got unimaginably bigger than anyone had assumed. But Hubble's real bombshell came a few years later, in 1929, when he noticed something stranger buried in the light from these distant galaxies. Their light was shifted toward the red end of the spectrum, and the farther away a galaxy was, the more its light was stretched. The only explanation that fit was one nobody had seriously entertained before. The galaxies weren't just sitting out there in fixed positions. Space itself was expanding, carrying them apart, and the universe had a beginning, rather than existing eternally and unchanged. Even Einstein, whose own equations had hinted at an expanding universe years earlier, initially resisted the idea. He'd added a fudge factor to his own general relativity equations, a term he called the cosmological constant, specifically to force his math to describe a static, unchanging universe, because that's what everyone at the time assumed reality looked like. After Hubble's observations, Einstein reportedly called that decision his biggest blunder. Decades later, that same abandoned cosmological constant would be dusted off and rehabilitated as one of the leading mathematical descriptions of dark energy itself, proof that even a mistake in physics sometimes turns out to be a genuine discovery, just decades ahead of the evidence needed to justify it. That discovery is the entire reason a cosmic horizon exists at all. If the universe has a finite age, then light from anything sufficiently far away simply hasn't had time to reach us yet, no matter how good our telescopes get. There's no way around that limit with better engineering. It's baked directly into the age of the universe itself, currently estimated at roughly 13.8 billion years. For decades, that's how astronomers thought about the horizon. a slowly, steadily expanding boundary, growing outward every year as more distant light finally completes its journey to Earth. Simple, predictable. The kind of story where you'd expect, given enough patience, to eventually see almost everything. Then, in 1998, two independent teams of astronomers studying distant exploding stars called supernovae found something that broke that comfortable picture completely. The expansion of the universe wasn't slowing down under its own gravity, the way everyone had assumed it should. It was speeding up. Some mysterious force, later named dark energy, was pushing space apart faster and faster with no sign of stopping. The discovery earned its researchers a Nobel Prize in Physics in 2011. And it quietly transformed the cosmic horizon from a boundary that only ever grows into something with a much darker second act. Here's the problem dark energy creates, and it's a genuinely strange one once you sit with it. Our cosmic horizon isn't simply an edge determined by the universe's age anymore. It's a battlefield between two competing effects, and one of them is winning. On one side, light from increasingly distant galaxies keeps arriving, technically expanding the theoretical maximum of what we could ever see, given infinite time and perfect instruments. On the other side, dark energy is accelerating the expansion of space itself, stretching the distance between us and every other galaxy faster and faster. And crucially, this acceleration doesn't just make galaxies look farther away. Past a certain distance, it means those galaxies are receding from us faster than light can cross the space between us and them. That's not a violation of relativity, strange as it sounds. Nothing is moving through space faster than light. Space itself is simply expanding, carrying galaxies along with it, and there's no speed limit on how fast space can stretch. But the practical result is identical either way. Once a galaxy's recession speed outpaces the ability of its light to ever close that gap, it is gone. Not too far to see yet, permanently, physically unreachable, forever. To put a number on how close this already is, astronomers estimate that, of the roughly 2 trillion galaxies within our observable universe today, more than 97% are already, right now, moving away from us fast enough that any light they emit from this point forward will never reach Earth. We can still see them, because we're watching light that left them long before this threshold was crossed. But new light, leaving those galaxies today, is already sealed off from us. The horizon isn't a future problem. It's already closed around the overwhelming majority of what we can currently see. This is happening constantly, right now, to galaxies we can currently observe. Distant galaxies are visibly redshifting and dimming in our data as we watch, slowly sliding toward the point where their light will never complete the journey. Current models are unambiguous about where this leads. Everything outside our own local group, the small cluster containing the Milky Way, Andromeda, and a handful of smaller satellite galaxies, all close enough and gravitationally bound, tightly enough to resist the expansion, will eventually cross that boundary and disappear from view forever. Sit with what that actually means for a moment. We are not living at some early, unremarkable chapter in an ever-unfolding story where there's always more to discover later. We're living inside what astrophysicists increasingly describe as a uniquely privileged window, a narrow span of cosmic time in which it is still possible to look up, see other galaxies, detect the leftover glow of the Big Bang itself in the cosmic microwave background, and actually piece together where the universe came from. That cosmic microwave background is worth pausing on, because it's arguably our single most important piece of evidence for how the universe began. And it's exactly the kind of clue a future observer would lose. It's the faint, ancient afterglow left over from roughly 380,000 years after the Big Bang. The moment the universe finally cooled enough for light to travel freely, instead of being trapped in a hot, opaque plasma. We can still detect it today, in every direction we look, as a nearly uniform bath of microwave radiation. It's essentially a baby photo of the universe, and because of the accelerating expansion described above, that afterglow is thinning and redshifting with every passing billion years, exactly like every other signal, drifting toward the horizon, heading toward the same fate as the galaxies themselves, eventually stretched beyond any hope of detection. Trillions of years from now, an observer on whatever remains of Earth will look up at a sky containing nothing but our own merged local group of galaxies, glowing alone in an otherwise empty, silent darkness. They will have no cosmic microwave background left to detect, no distant supernova to measure, no redshift data to analyze. Every clue currently available to us, sitting in plain sight in tonight's sky, will simply be gone, and they will have absolutely no way of knowing that any of it was ever there at all. That raises an uncomfortable question that cosmologists are actively grappling with right now. What information has already crossed that horizon and vanished, forever lost to us, before humans even existed to notice it was there? We don't know. We can't know. By the very nature of the problem, anything already gone left no trace behind for us to notice its absence. Faced with a horizon that's actively shrinking and permanently erasing information as it goes, astronomers had to make a choice about how to spend their limited window, race the clock by pushing observations as far back in time as current instruments will allow, or try to mathematically infer what lies beyond the horizon entirely, using the universe we can measure as a guide. Both paths are being pursued simultaneously, and both delivered genuine breakthroughs recently. The first path, pushing observations as far as technology allows, belongs to the James Webb Space Telescope, and it just rewrote the record books. In confirming the discovery of a galaxy designated MOM-Z14, JWST detected light that had been traveling toward us since the universe was just 280 million years old, at a cosmological redshift of 14.44, deeper into the past than any previous confirmed observation. For context, the universe is currently 13.8 billion years old. This is a snapshot from when it was barely 2% of its current age. Here's where the decision to keep pushing paid off in a way nobody predicted. Theoretical models had confidently forecast what astronomers should find at that extreme distance: a dark, cold, primordial fog, mostly plain hydrogen gas, with only the earliest, faintest hints of structure beginning to form. Instead, JWST found a galaxy that was bright, massive, and chemically enriched, meaning it already contained heavier elements that are only supposed to form after generations of stars have lived, died, and seeded their surroundings with the byproducts of nuclear fusion. That kind of chemical complexity this early shouldn't have had time to happen yet. And consider the timeline problem this creates. Stars need to form, burn through their nuclear fuel, and explode as supernovae before they can seed their surroundings with heavier elements. Then, a new generation of stars needs to form out of that enriched material and produce more of the same. That's normally assumed to take a meaningful chunk of cosmic time to unfold even once, let alone enough times to explain the level of chemical enrichment found in a galaxy only 280 million years removed from the birth of the universe itself. Either that entire cycle happened far faster in the extreme density of the early universe than anywhere we've observed it happening since, or our models of early star formation are missing something fundamental. It's the same kind of problem you've heard in this series before, applied to an entirely different corner of the universe, a structure that grew far faster and far more violently than our models say it should have been able to. Just as TON 618 forced astronomers to reconsider how quickly black holes can grow in the early universe, MOM-Z14 is forcing them to reconsider how quickly galaxies themselves can assemble and mature. The edge of our observable horizon, rather than fading into the simple fog theorists expected, keeps revealing more structure, more complexity, and more unanswered questions the closer we manage to push toward it. The second path, inferring what lies beyond the horizon entirely, doesn't rely on better telescopes at all. It relies on geometry. To understand what might exist beyond the part of the universe we can ever hope to see, cosmologists turn to a question that sounds almost absurdly simple. What shape is the universe? Space, according to general relativity, doesn't have to be flat the way a tabletop is flat. It can curve. A universe with enough matter and energy packed into it would curve back on itself, like the surface of a sphere. Travel far enough in a straight line in that kind of universe, and you'd eventually loop back to where you started. A universe with too little matter would curve the opposite way, like an infinite saddle, stretching outward in a shape called hyperbolic space, and a universe with exactly the right amount of matter and energy would be flat, extending outward with no curvature at all, the geometry you learned in school, where parallel lines never meet and never converge. For decades, measuring this precisely was almost impossible. But by combining data from telescopes observing the faint afterglow of the Big Bang with newer measurements from gravitational wave observatories, cosmologists have been steadily tightening their estimate of the universe's overall geometry, alongside a related and equally contested number called the Hubble constant, which measures exactly how fast the universe is expanding right now. Gravitational waves, first directly detected in 2015, turned out to offer a genuinely independent way to measure cosmic distances. Colliding neutron stars and black holes act as what astronomers call standard sirens, producing a wave signal precise enough to calculate distance without relying on the same assumptions baked into older, light-based methods. Where the two techniques still disagree slightly on exactly how fast the universe is expanding, a persistent puzzle known as the Hubble tension, they agree almost perfectly on the deeper question of the universe's overall shape. Current data is remarkably consistent on one specific point. The universe is flat, to within a fraction of a percent of perfectly flat. That single geometric fact carries an implication far larger than it sounds like it should. A perfectly flat universe, under general relativity, isn't a bounded shape that curves back on itself and closes off somewhere out of sight, the way a sphere does. It has no edge to loop back around, and nothing in the mathematics requires it to stop existing at any particular size. The leading implication, taken seriously by cosmologists working on this exact problem, is that space simply doesn't stop. What lies outside our cosmic horizon isn't a boundary followed by nothingness. It's mathematically indistinguishable from an infinite continuation of the same universe we're already living in. More galaxies, more clusters, more of exactly the kind of structure we can already see, stretching outward without end, forever beyond anything we could ever hope to observe directly. Picture what that actually means, held next to everything from Act 3. We are right now living inside a finite observable bubble of a universe that may genuinely be infinite, surrounded by a horizon that is actively shrinking, cutting off access to more and more of that infinite structure with every passing year. Somewhere out there, past every galaxy JWST has ever photographed, and every galaxy it ever will, more of the exact same universe almost certainly continues. We will never see it. We will never prove it directly, but the shape of the space we can measure says, with as much confidence as science currently allows, that it's there. Here's what I keep coming back to with this one. We're used to thinking of exploration as a story that only ever expands. More territory mapped, more distance covered, more of the unknown steadily converted into the known. The cosmic horizon breaks that assumption completely. This is a frontier that closes as it opens. Every year, JWST and instruments like it manage to push our view of the past a little further back, revealing structure and complexity nobody predicted. And every year, dark energy quietly erases a little more of the present, carrying distant galaxies past the point where their light will ever reach us again. we are simultaneously seeing further than we ever have and losing access to more than we ever will get back. That's not a reason for despair. If anything, it reframes something we usually take completely for granted. Right now, tonight, we happen to be living during the one stretch of cosmic time when the sky is still full enough to actually study. Full of galaxies close enough to observe, faint enough afterglow left over from the Big Bang to detect, and just enough clues scattered across the visible universe to reconstruct where all of it came from. That won't always be true. It wasn't always true either. Trace things back far enough, and there was a point when even asking the question required light that hadn't finished arriving yet. We are standing inside a narrow, temporary window where the evidence still exists to be found, and we happen to be the ones holding the instruments capable of finding it. And there's something almost hopeful buried in the flatness measurement if you let it sit for a moment. The same universe that's actively hiding its own history from future observers is, according to its own geometry, almost certainly far larger and far richer than anything we'll ever manage to see. We're not running out of universe. We're running out of access to it, which is a very different and slightly less bleak kind of ending. It also reframes what a discovery like MOM-Z14 actually represents. It isn't just a new record on a leaderboard, pushed back a little further with each new instrument. It's a message arriving from a part of the horizon that's actively working against us. Light that managed to complete an almost 13.5 billion-year journey, informing us of exactly the kind of complexity that the expanding gulf of space is otherwise conspiring to keep hidden. Every confirmed galaxy at the edge of what JWST can see is a small temporary victory in a race we already know. Eventually, we lose. So somewhere beyond the edge of everything we will ever be able to observe, more galaxies are very likely still burning, more structures very likely still forming, in a universe that may never actually end at all. We will never see it. But right now, in this brief, privileged window, we're close enough to the edge to know, with real confidence, that it's there,